Thank you very much for being here this morning. We are looking forward to the next talk in our learning seminar by Tongmu He, who is going to explain us the local p-adic Simpson correspondence, layer twisting, and geometric Sen operators associated to pro-étale.
Thank you for your introduction and thanks for coming to my talk. So first, I will fix the following notation in the next 2 hours. So let K be a algebraically closed, complete valuation field of height 1, and which is an extension of QP, and let X be a proper smooth rigid analytic variety defined over K. And I will simply use this notation, omega x tilde, to be the tail twist of the module of differentials. And I will denote by Tx the symmetric algebra over Ox of this vector bundle, the dual of omega x tilde. So this is the tangent bundle, and I denote by nu the projection from the pro-étale side to the étale side of X. And so first, an overview. The goal of our seminar, I think, one of our goals is to establish an equivalence of category from the category of vector bundles over the pro-étale side of X to the Higgs bundles. Over the étale side of X. So recall that Higgs bundle is a pair where E is a vector bundle over X, and the theta can be regarded as a homomorphism from the dual of the differential to the vector bundle of the endomorphism of E. So we could also regard the theta as a global section of X to the omega x tensor with this bundle of endomorphism of E. Okay, so how do we establish such a p-adic Simpson correspondence? So I think the basic idea is it starts from Heuer's observation of the multiplicative Hodge-Tate sequence. So let B be a coherent OX algebra, and I denote by curly B to be the pullback of B over the pro-étale side. So for example, a typical choice of such B is the sub-algebra if you fix a Higgs bundle, and we consider the sub-algebra of the endomorphism generated by the image of the Higgs field. The image of the Higgs field. So I should write. Yeah. Okay, so if we have such a coherent OX algebra, then there is a short exact sequence from the pika group of X, from the first identical module of X with coefficient in B cross, and you pull back to the pro-étale one with X, and then we use the curly B cross And then finally, we have a log version of the hot state map to the differential. Okay. So the idea is that splitting of such a short exact sequence can be regarded as an coordination of a p-adic Simpson correspondence. So, namely, if we have a lifting, have a splitting, for example, if I split for every Higgs field here, I can take something called L theta here, then we can have such a decomposition to so sending a pair, a vector bundle here, and theta, because a Higgs bundle can be regarded as a B module if you take this B to be the subalgebra generated by the Higgs field. The Higgs field with the X on E, so the vector bundle E could be regarded as an element here. So everything here is very rough. This is just to give an idea. So the decomposition will give you the functor like this. You pull back this bundle, and then you tensor over this curly B with this invertible B module. Okay. So so you see that if we have a Higgs bundle whose whose Tx action factor through this algebra B, then we can have this decomposition. And if you vary this B, then we could cover all Higgs bundle. Then we can get a correspondence for all Higgs bundles. So, any question?
So what are the assumptions in B for the sequence to be surjective?
So when X is proper, then this is surjective. In general, this is not surjective, but only left exact.
So if B was like a skyscraper sheet, would this still be true?
Sorry? Coherent OX algebra?
Right, could be like the skyscraper shape at a close point.
I think this is true. Let me check his paper.
Actually, it couldn't be that because the name is a vector model. I mean, but maybe.
Right, I'm asking if the example is an assumption or an example.
But I think he states that this is true for. Yeah, I think this is strange. Yeah, I think he claims that this was for any coherent OX algebra. The proof for the left exactness is kind of easy, but for the surjectivity.
If B was the coordinate ring of a curve that was finite over X, which is a curve, then wouldn't you expect the target to be like differentials on the curve on top?
Tensor B
It's not
tensor
gonna be the same.
they already tensor this B, right?
What's that?
Already tensor this targeted tensor already tensor.
Don't
Yeah.
you need that it's
But I guess I'm confused about that.
it's an algebra, I mean, it's a metric product of this omega.
But I think for this, we don't need B to be. Yeah, probably we need to add some conditions on that. Which is a TX algebra and OX coherent. But I don't know if this will release your concern.
Sorry, I'm just like in the stupid example of B is a skyscraper sheet. I would have guessed that the H1s were both 0, but the H naught is non-zero. I think in his paper maybe he also assumed OX, it is OX torsion free.
Yeah, but I think when he proves this proposition, he didn't assume this is OX torsion free.
For us, do we only need the
Yeah, I think for us we need, yeah, we only need the OX torsion free case, but yeah. Yeah, sorry for that. I didn't check completely the. Okay, maybe we move on. Okay, so we would like to find splitting of this multiplicative Hodge spectrum sequence. The existence of such a splitting, however, use the following key ingredients. So first, we can pick a lift of x to b plus from modulo cosine square. Cosine is the generator of the kernel of Fondant's theta map. If you have such a lifting, then you can construct the mixed state tensor of a basic Hall. Then you can get a splitting of the Hodge sequence. Namely, this is the splitting on the level of the algebra. Okay. And the second step is that we fix exponential extending the usual exponential map from k to 1 plus the maximum ideal of k. Then a theorem of Artin's says that once you have this choice of exponential, then you can have a similar exponential for class of certain commutative rigid groups. Then, combined with this splitting of the Lie algebra level, we get a splitting of the multiplicative Hodge sequence. So, but notice that to upgrade to a functor between categories of Higgs bundles and vector bundles instead of just the isomorphism classes. So we should pick this L theta as a specific invertible B module instead of just an isomorphism class, which is an element of the cohomology group. So L theta should be a specific invertible B module. So then we have the how to pick such a specific B module. Then this is the third ingredient of the proof, which is Heuer's ingenious, I mean, it's very ingenious to me, rigidification of these pro-étale bundles. So, okay. Rather than this homological group. Okay, so all of these key ingredients defining Simpson functor will not be discussed today. Hopefully this ingredient will be discussed next week. So today we will only present key ingredients to prove that the essential surjectivity of inverse of this functor. Okay.
Wait, sorry, I just wanted to say I would draw my objection from before. I think the torsion freeness is not necessary in my counterexample. It doesn't work with.
Okay, so it works for every coherent OX.
At least for the skyscraper shape, it works. Is that pro-étale H1 is not zero.
Yeah. So to prove, first we only construct if we have a Higgs bundle in hand, then we construct what's the corresponding vector bundle over pro-étale site to it. So as I said, we need to pick specific invertible B modules to complete such a decomposition. And when you vary B, when you vary the Higgs fields, then you should pick compatible system of such specific invertible B modules. So this is to prove the existence of such compatible system of specific invertible B modules, this is a theorem of Heuer. So let's I be the filtered category of Tx adverse B on the étale site of X, which are OX coherent and OX torsion free. So this is the category of all such Tx integrals. Then there exists a compatible system of invertible this curly B, which is the pullback of all of such B lies in this co-filtered category. A compatible system of such B invertible B modules on the pro-étale site. So I denoted by LB. Satisfy the following conditions. So for every map of Tx algebra in this category, then the transition map from LB prime, and you tensor B prime, you pull back to B, and to LB, this is an isomorphism. So all of these transition maps are isomorphisms. And the second, so for any such Tx algebra B here, I consider the special element in the global section of X with the coefficient in omega X tensor B. So this is just the element defining the corresponding to the canonical map from the dual of X to Tx to B. Because B is a Tx algebra, so Tx maps to B. This is the structural morphism, and Tx is the symmetric algebra of these Lie algebras. So we have a map from this Lie algebra to B. So namely, this morphism gives you an element of the global section of omega X to the tensor B. Okay. So this is the special element associated to B. I call it theta B. Then those invertible modules satisfy the following condition, that if I consider the Hodge-Tate log map to this, it will map the isomorphism class of LB to theta B. Okay. Any question for this statement of the theorem? So as I said, yeah. So namely, he can, when you vary B in this category, then you could pick compatible such splitting. And every LB is a true invertible module instead of just an isomorphism class here. So as I said, to establish such a existence, Heuer pick a lift to get a splitting of Hodge-Tate sequence and fix this using Falkin's exponential to get a splitting of Hodge-Tate log sequence. Then by adding his rigidification, then he kills all the isomorphisms. So then he can obtain the true invertible modules. Okay. Any question?
So this theory is what noted by 3 above.
I mean, this theorem is the combining of 0, 1, 2, 3, the 4 ingredients. Yeah.
And there is some unicity or...
No, in fact, there are infinitely many such compatible systems, but all of them are isomorphic to each other, but not uniquely isomorphic to each other. Yeah. I think this is the heart of the story. Should we move on?
Sorry, so is the idea that each choice gives an equivalence?
Yeah, I think yes. If you can pick such a compatible system, then you obtain a functor. And for if you pick different compatible system, there exists some isomorphism between each other, but not unique, not canonical. So in fact, there are infinitely many such functors isomorphic to each other, but you couldn't pick a canonical one. So my understanding is that every such data will give you a functor like that. So the functoriality of this p-adic Simpson correspondence is very complicated.
So then when you do these twists, you get things that come from the analytic site, right?
What do you mean? You mean twist what?
To twist B by this line bundle.
Twist B by this line bundle.
That line bundle was the obstruction to.
Yeah. If you start from something here, then you twist. If you start from a pro-étale thing, and you consider its image, and you twist it by the inverse of L theta, then it comes from analytic site. Is that what you mean?
I think I'm confused.
This last thing, you are sending LB to theta B.
Yeah, the isomorphism class of LB to theta B.
Is it LB fixed?
LB fixed. I mean, there exists such a compatible system satisfying the two conditions.
But wait, what's the quantifier here? Don't you have to fix theta B first in order for this to have a chance?
So for any B, theta B is the canonical element here, which corresponds to the structural morphism of B. So for every B, which is a TX algebra, so there is a structural map from TX to B. So Lie algebra maps to B because TX is just a tangent bundle. So such a structural morphism associated to a canonical element associated to B. And I require that our picked invertible module has the architect log image theta B. Yeah. And for each theta B is like a Hitching base. So for each B is like a Hitching base. And yeah, we just need, for over each Hitching base, I pick invertible module LB. And I need that for different Hitching base, they are compatible with each other. So that I could define a compatible, a well-defined functor of all Higgs bundles.
So could I ask, is there a particular I which I should keep in mind?
I mean, I is the category of all of these TX algebra B.
But you said that you wanted to be confiltered, or?
Yeah. So you can keep this in mind if you have B1, B2, such two TX algebra, and you consider their product. So it enlarged the Hitching base. Or you can regard this like this. You can so intuitively B1 corresponds to the endomorphism of a Higgs bundle E1 theta 1, and the B2 corresponds to the endomorphism of E2 theta 2, and you can combine them together by direct product.
Are you explaining now that I'm allowed to take I to be all such B?
I think maybe perhaps what surjections of this, I'm not sure.
I didn't specify to only surjections. So the morphism in this category are all TX algebra homomorphisms. And this thing makes it, this thing tells you this is a co-filtered category.
Do you want to take equalizers as well?
Yeah, I would like to take equalizers because, for example, I have TX mapped to here, mapped to here. I would like also, I take the image here. Like, yeah, I also allowed to take the image of TX here.
And also, what happens if you take tensor products of two such algebras?
Tensor products, I think that's it's not in the direction of this I. I mean, tensor product goes that way, but I need an inverse direction. So namely, I just disjoint union of all of the Hessian base together. Yeah, and I just consider we gather together all the Hessian bases in disjoint unions, but I just couldn't take the colimit because it will give us integral algebra instead of just the finite algebras over OX. Yeah, because this thing only proved for finite OX algebra, so I couldn't take the colimit of the limit of all of these things. I could only, yeah, state things like that.
I misunderstood.
Something that lives on the formal completion of the cotangent bundle along all multi-sections.
Maybe, yeah, you could imagine like that. Yeah. So then with this, if you pick such a choice, then you can define the p-adic Simpson functor. So for any Higgs bundle on X. So for such a Higgs bundle, I can take B to be the image of the Higgs field. Higgs field is just a map from the tangent bundle to the endomorphism of E. I take B to be the image of that. Of course, this is a locally free OX algebra, so B will be OX torsion free, and also it is coherent because this one is coherent and finally generated. So yeah, so such B satisfied lies in this category. Okay, so I take B to be the image of that. Then we can put, we set S inverse defined over this Higgs bundle is just we pull back E to the pro-étale side and we twist by this special invertible B module. So this is a vector bundle over X pro-étale. Okay. So although I do not want to bother you, but I still need to remark that the construction of B is not functorial in this Higgs bundle. Thus, a priori, S-1 is a priori not a functor. But I think we will see next week that we can make S inverse a functor.
Isn't it not important that you get exact compatible B's? Can't you like take the loci like you're doing there?
But yeah, I don't know. This is the presentation of his paper. I couldn't make more. Yeah, but anyway, you can omit this warning, and we will see next week to see how we'll make this inverse S to be a functor. In fact, it's in particular for B1 and B2, you use these to compare their definitions, something like that. Okay. Okay, so we move to the main topic today, the local correspondence. The local correspondence is the key to prove that this S inverse is indeed essentially surjective. So let me fix some notation. So let U be an affinoid rigid space over K, and with F from U to I should write down. I have no spaces. With the map F from U to torus which is a composition, which is standard data. So namely, it is the composition of rational localizations and the finite data map. Morphisms.
Where's our this?
So, sorry?
Yes, in virtual.
Yes, I'm sorry. Okay. So now I can pick the usual tower. Infinity, which is just the spar of K. You add all p power roots to that. And similarly, you have OK here. So this will be a pro-étale delta tosser. So this delta is isomorphic to the D direct product of CP Ted twist. Okay. And I consider the fiber product. So this is also a delta tosser over U pro-étale. Okay. So the local correspondence is essentially due to farthings, and Heuer modified his proof to his situation. So let's look at how we get a local Simpson correspondence in this setting. So first we look at our object on the left-hand side, which is vector bundles over U pro-étale. Okay. And so by a theorem of Kalaya-Liu, we know that these are just finite projective continuous representation of this delta with the coefficient in the structure in this O U infinity. So namely, for any vector bundle, I just take its evaluation on this perfectoid cover. So I will get a continuous finite projective representation of delta with the coefficients there. So in fact, this explains that why we call the pro-étale vector bundle a generalized representations. It's just a sheaf of representation of local Galois groups like that. Okay. Okay, so now I specify a full subcategory. So there exists a constant C, which depending on F and I consider all the so-called C plus small representations. So I will give you the definition. This is just the full subcategory formed by objects formed by representations lying in the image, whose isomorphism class lying in the image of the continuous Galois cohomology of delta. You consider the identity plus p to the c plus and you times this O plus to the continuous cohomology of delta with GLN. So here PC plus is just the PC times the maximal ideal of K. Okay, so this Galois group cohomology classify all the finite free continuous representation here. Okay, and I only consider those representation which has a good integral model. Okay. So by consider such C plus, we can also consider the C plus small representation down of this Galois group, but I simplify the coefficient. So here you see that delta x also owns this coefficient here, delta x here. But I don't want that, it's too complicated for me. So I just simplify its coefficient here, down. So, and there is a natural functor given by base change. Okay, so it is contained in the representation of continuous finite projective coefficient. Okay. So the key theorem is that every C plus small representation descends to that. So this is an equivalence of category. This is a theorem of Martin's, and Heuer modified his proof to this situation. So this is the descent of representations, which appears also in Sen theory and a lot of things. Okay, any question?
Sure.
Yeah.
Is it true that like the smallest condition is the same as having all plus model such that modulo some power of p it's trivial, or is it different?
Sorry, could you repeat again?
Or just on the level of vector bundles, is it the same as having an O plus model such that modulo, I don't know, p to the power of c or some c prime bigger than c, it becomes trivial?
Yes.
Yes. Because this is just the co-limit of all identity plus p c prime. Yeah, and c prime is bigger than c.
Okay, but I mean, is it like that you only have almost vanition for cohomology doesn't cause any problems, right?
Sorry, almost.
Anyway, sorry, I can.
What is your C?
There exists such a constant c depending on f. Okay, so if we have such a descent theorem, then we can see easily that this is equivalent to C plus small X bundles on U eta by sending a X bundle to So I keep this bundle here. So here E is a free vector bundle. But this is the definition of smallness. And I handle it with a Galois action of theta. So this theta will give you by coordinate theta I. If you evaluate theta to this derivative, this will give you an endomorphism on E. Okay. And I can pick the ith generator gamma I here, because theta is canonically isomorphic to CP1 twisted by 1. And so this one acts here by the exponential of theta I. Okay, this is and one can see that this is an equivalence very easily.
Okay. Sorry, so these are small Higgs bundles. Maybe could you define that?
Yeah. I think it's just there is an integral model such that theta acts on it by yeah.
Sorry, no, I got it.
Yeah, you're right. So in conclusion, so there exists a local Simpson correspondence depending on the choice of this. I will call this such a map by toric chart. So on this toric chart, we have a local Simpson correspondence from our C+ small Higgs bundles. On U-étale to C+ small vector bundles on to pro-étale. Okay. Any question? So an important remark to control this constant. Otherwise, if we couldn't get control of such constant, then we don't know which kind of vector bundle are locally small, right? So we need control of such constant. Saying that if I consider the finite tower in this perfectoid cover, for example, I only add the p to the nth roots of ti's, so I call it tnd, and I consider this finite cover is fn. This is n. This is f. So fn is also a toric chart in some sense, in the above sense. So the remark is that the constant he constructed for fn can be taken strictly less than the constant C for f. Namely, if you have a general finite free delta representation over U. Then by going up to this tower, you will see that the Galois group shrinks. So, but however, the smallness bound will not change. So namely, if you start with any finite free representation of U, by going up this tower, it becomes small. Okay. Because when delta becomes smaller and smaller, then a representation will lie in the image of that.
Can you say a few words about the sensory step?
This is quite, yeah. I mean, in sensory in any p-adic couch theory, this descent step is necessary, right? It's just, sorry, I'm too ambiguous. So in set theory, we also have such a descent, a similar descent step to define the Sen operator. And the Sen operator, you will see that it is the geometric Sen operator is exactly the Higgs fields. You will see later, I think.
I'm confused. So why doesn't this remark mean you get to remove the smallness from the?
So if I couldn't get control of the constant here, so you start from a representation over U. You start from a representation here, and you consider its restriction of the smaller Galois groups. The constant changes, right? So you might see that it will never become small when you pull back along this tower. But once we have this control, then you will see in sufficiently large step, you will get a small representation so that you could use this local correspondence.
But then why does once you know that?
Correspondence doesn't descend.
What's that? It does. The Higgs structure doesn't descend that finite.
I think you can make it small by passing to some cover and then use the correspondence there, but it doesn't descend.
So you want if you first make it small and you descend. I think this is the first strategy of Martins to establish the whole p-adic Simpson correspondence. But this step is quite is subtle. Why is that? Because you see a local correspondence depending on this chart. So when you descend it, it's not canonical. You could descend, but it's not canonical. And once you pick the compatible system of L theta and you formulate things like that, you can get some canonical correspondence.
Wait, what in this picture is not canonical?
Sorry?
What in this?
I think identifying with Higgs fields, right? Like Ti will now upstairs become Ti to the 1 over T to the n.
That's that doesn't feel so bad.
Okay, so this remark implies that everything is locally small. So let U be a smooth, rigid space. I didn't assume proper here. Okay. Then for any vector bundle V, pro-étale vector bundle on U, and respectively, we could consider the Higgs bundle. It's on U eta. There exists an étale cover. U to ui to u, with each ui a toric chart. Such that the pullback of this pro-étale vector bundle to ui, respectively, you pull back this Higgs bundle to ui, then it is C depending on Fi plus small. So everything is locally small. Okay. Any question?
I'm still confused. So the C in the theorem of Hawking's, how is not a uniform constant?
It's not because something like that. If you consider semi-stable case or just the smooth, if you consider an algebra smooth over OK, formally smooth over OK, and you consider and it has a chart like that, and then you can the smallness. Then in this case, you can always pick C to be 2 over P minus 1. Okay, yeah. This is in Farting's work. Yeah. But now things is a little bit different because here is bar A. If you consider something like that, so here A invert P is finite-étale over R invert P, and A is the integral closure in the finite-étale cover. If you consider this case, then the constant for A will be changed because of some, yeah, anyway, it will change. So yeah, this appears in many work. Yeah, CR is this, the CA. We will not be bounded by CR.
Is it true a priori that somehow it's always coming from H1 continuous of delta into something like identity plus P to the 0 plus? Meaning, is there always some O plus structure such that while max might do its count, the trivial?
No, I don't think so.
Then how can I see that by passing to a smaller subgroup, I will get arbitrarily?
Sorry. So delta is continuous, right? For example, if you use some notation like that, delta is continuous means that there is an open subgroup whose image lies in this open subgroup, right? Because these are the open subgroup of that.
Theta I, what's supposed to correspond to d by ti or ti d by dpi?
Sorry?
Right.
You mean this one?
Yeah.
This is a basis of.
But it's not the translation invariant basis.
So you mean I should consider the dual basis of something like the dual basis of this one, right?
Yes.
Yeah, maybe, yeah. So that's my mistake. So theta I should be theta evaluated at d log ti, and you consider the dual basis of that.
I think that's just ti times d by dti, right?
Yeah.
Yes.
Okay, maybe we take a break for 10 minutes.
That's all fine.
Those get fine.
这个 CN 也只能保证小一点，也并不能保证它会。
反正你可以取小一点的。
不是我讲说这是可能就是说 ，OK， 就是说你有一个bundle，然后你要取个 coverage， 然后在每个局部都很小。OK， 我可以想象就是说，当然可以使这个 bundle 变小，但是你怎么能你为什么可以让变小呢？使得它满足这个 CFI 小，因为你这个 CFI 你并没有办法。
首先我可以随便取一个 cover，
对，
随便取一个 cover， 然后你可以这个 CFI 可能很大，然后我的 restriction 可能不小，对吧？
对。
但是我可以把 UI 换成这样的 cover，
对，
然后它的那个 CFI 被控制住了，它的 CFI 和 CFIN 是一样的，你可以认为它们是一样的，好吧
？OK， 这个 CFI 没变
，CFI 没变，然后但是呢，它的 Galois group 缩小了，
对，
所以它就变小了。
它这个 C 这个东西，我就是看见它这个文章，就是说它这个就是那个这样的文章，这个 C 用这 2D 这篇文章，
对，
但是它这个首先它这个定义定义是
6.1，它这个定义有问题，我跟他讨论过。
确实不是 uniform
对，因为它也写了不是
这个第一个 C 是好像看这样这跟 G 有关系。这是5.5点，这是那个他要的那个 C 吗？
别人他写问题，他也是 G。它不只跟 G， 它跟
X 也有关系，
它跟 X 肯定有关系，对 X 应该只是一个 toric chart。
就是说
他们不能够是
Okay, sorry. So what's the precise argument?
那个是可以啊。不讲了。
让他讲。对，刚刚又回来，就是说你这个 S 这个方式，感觉好像你现在讲 S inverse 是吧？
对
，S inverse 这个东西还可能就，但是还有直接定义吗？有出来的定义
S 我一开始给的定义。S inverse
我说 S 呢？
S 等会儿我也会给个定义，你要用3 operator 去给定义。但是我突然觉得 small 这有点问题。
对，
它不应该 integral model 不应该是 free 的吗？
But that's not
my feeling is that equivalence between
control map from D to 3 and then D of A quasi-core protected.
Construction is just by.
Do you have a map?
这不就是他写的吗？
Yes, so.
It's right.
就在这样。
Well, there are many more.
6.4当初最正好的就是这个定义。对。
This also can be identified as models of a certain algebra,
When you go up,
which is endomorphisms.
change the basis that you've chosen from PG differentials by rescaling.
Yeah.
But you
Just
also
like what was things.
change the group delta.
我当然没 check 过，但是写文章的时候也写过类似的东西，所以我觉得它应该是一个。
Then what we were thinking with
但是他这篇文章我觉得题材非常麻烦，我觉得没省个2个。
yes, it's
Well, I wanna, I just said something
So Minja and I actually thought about that for a while.
It's
哎，但是我觉得，突然间想到，ABS E small 的时候，是要求 integral 才能但是它这里是要求，对，它这个很强。
So if you use
因为 ABS 后头是就
over
不要就反正这差别很大。
在我刚刚写着，我就突然
对，所以我就看到这个
Scala I put very effort.
может показать.
我突然一下有点害怕。
One of them is a lattice in front of the other.
Нет, то есть там
哎，我不记得了，我去复习一下，我是一年了。
but what you want to do, if I understand you correctly, you want to have the correspondence there. You want to present the correspondence. Yes,
那个绝对是他的绝对就是我觉得这篇文章的唯一亮点，也不是说唯一亮点吧，就是让我想起就是让我觉得真的是豪尔的东西给一个他那个选的太妙了。
但是怎么想主要想法是什么？
主要想法，我这我也不好说，还是得自己看一看。
很奇这个让我想起就是三 Siri 那篇文章，我发现那个文章，
他那个跟他做法不一样。
不，我知道，我就说三里面它有一个结果，这个很奇怪的，就是三是什么结果呢？三里呢是说从一个 C 表值得到一个 x 的加上 n 的模倍，对吧？然后三这里呢是但是这个东西就是这个 map 显然一般也可能不可能是一个问题。
I think the question is
三这里呢是说这个
the situation where you have
只有 ultimate close，
that you get an equivalence between Higgs bundles.
这个时候你可以乘上
a function
是我知道
pro-étale bundles on you.
然后这个构造是也是它那 long canonical， 并且那个 equivalence 它不可能是 tensor compatible， 所以但是 OK， 但是我知道这个 S 确实是 tensor compatible，
是，
但是好像就是说你这个地方也是要对这个它
You need to let U and
那个
对的我知道不一样，
但是这也是要选一堆东西。
对，它难道表？难道是做 P 之后谁怎么选？难道是对 simple 的 theta 去做选取吗？还是它当时是怎么选？
没有，就每个 theta 都
That changes delta, but it also changes that basis that you've chosen for the differentials. And doesn't that?
You can define the Higgs field.
What's that?
Given a V-vector bundle, you can define Higgs field and locally it's that.
Yes, X field for V bundle. This is canonical. Yeah, but if a data bundle is not, it depends on.
Wait, so what have we done here? So we
obtain Higgs bundles on U, but if you pull back to U infinity, pull back if theta to U infinity, and this is canonical. And then the more valuable we can third action. And you can also reference to canonical Higgs field for V bundle. Higgs field is bundle.
I think Jacob was thinking about the atomic. So you were thinking about these things, which are one of the. They depend. I mean, maybe this is which is hard to describe, but if you write it down and you have diagrams, you see that going this lattice.
Okay.
Maybe later we have to take Okay, but maybe we can continue this discussion over lunch and give Tongmu now.
Okay, so we have seen this local correspondence, and before recall that we define a global correspondence using this simpler form, right? And we would like to compare them. So this is the following proposition. And in fact, from this comparison, you could get a feeling that one could not glue all of this local correspondence. So again, let U be a phennoid rigid space over K with a toric chart. And let B be a OU coherent TU algebra. TU is the tangent bundle of U. And I give invertible curly B module with the Hotted log image of L to be the canonical element associated to B, which is element here. So then there exists. In fact, so we want to compare such thing with such thing, but in fact we couldn't compare them over U, but on a italic cover over U. So there is a italic covering. U prime to U. So this only depending on CF plus small Higgs bundle in theta whose TU action, the TU action given by the Higgs field of E, whose TU action factor through B. Namely, this Higgs bundle can be regarded as something over this Hitching base. Then for all of such small Higgs bundles over this Hitching base B, then there exists a natural isomorphism. There exists isomorphism lambda from, if we first do the local correspondence over U prime, and then restrict to U prime, then it is isomorphic to such a thing. This is functorial in all of such Higgs bundles. Okay. So remark is that such U always such. So if you have a coherent algebra B in hand, then we would like to pick such an invertible B module with the specific hot-state log image. This can be taken a locally. Such L exists, always exists after replacing U by UN. UN is the tower given by the toric chart. So again, this is something making smallness so that I can split this log and the hot state. Okay. So this is such a remark. So the idea to prove they are equivalent to each other, then we just so the idea of proving that is to use the Higgs state tensor of Abesco to give a concrete computation of the representation structure on both sides, and then you find they are equal to each other. In fact, the idea is that you can replace U by UN, then you can take Higgs state tensor of Abesco. Higgs state of Abesco give you a splitting of the hot state map, so you will get a invertible B module L prime, and you will see that L prime and L are ideal local isomorphic to each other, so that by replacing L by L prime, then you can get this explicit computation of L prime, so you will get this comparison. Yeah, I mean, this is a little bit technical. Any question?
Yeah. So for this remark, you say such L always exists. So if this exists for any B, you don't have any condition on B.
B, what is B?
B, yeah, the B in your.
Oh, B, yeah, B is just so if you have such B, then you have such a canonical element here. Then you restrict U to a dollar open like UN. Then L exists over UN.
But for example, do you have to assume B is torsion free?
I don't think so. Torsion free is only works for the rigidification of power. Yeah. So we have such a comparison. So you see that over U we couldn't get. It seems from the proof that we couldn't get the comparison between each other because L. There are many choices of L. Right? And, yeah. Okay. Okay, so that's what I want to say about local correspondence. Now, the last section is geometric sign operators. So we would like to prove the essential surjectivity of this functor S prime S inverse from the Higgs bundles to vector bundles over X pro-étale. So here we have E theta. We wonder if any vector bundle comes from such a Higgs bundle. That's our question, right? So, namely for any vector bundle V on X pro-étale, how to write it? as namely how to read this twisting torsor, this invertible D module. Recall that this is Hodge-Tate log image is the Higgs field. So how to read the Higgs field from V itself? We can see that, I think this observation, there is a very simple observation, is that because theta on E is just a Tx action, right? So the Higgs field is just a Tx action on E. And Tx is or I could say it is such a Lie algebra action. Such a Lie algebra acts on E, right? Theta is just such a Lie algebra action on E. And this Lie algebra is commutative. So this is a trivial Lie algebra. So the Lie algebra action commutes with the Lie algebra action itself. So namely, this Lie algebra action is not only endomorphism of vector bundles, but endomorphism of Higgs bundles. So as long as you have a p-adic Simpson correspondence, this Lie algebra action will transfer to Lie algebra action here. Okay? As long as you have a p-adic Simpson correspondence, this Lie algebra action will give you a Lie algebra action on V, right? This is canonical depending on the p-adic Simpson correspondence, right? So this is our observation. If V comes from E theta, then it carries a Tx action. So question, can we define it? Can we define this Tx action without assuming any correspondence result? Okay. So the answer is yes. So we have such a theorem. So let U be a smooth rigid space over K. Then for any vector bundle V on U pro-étale, there is a unique or canonical Higgs field for the theta V from V to V or U, and you pull back this differential. Namely, this is just a TU action on V, such that satisfying the following conditions. For any morphism and any isomorphism of the form V restrict to U prime, if I have such a, if I can write V as a twist by a étale vector bundle for so here for some OU prime coherent TU algebra B and some invertible curly B module L with conjugate log image to be the canonical element. And some Higgs field, Higgs bundle. Theta E, whose TU prime action vectors through B. Okay, so this is a little bit complicated. It means that if I did it locally, I can write our vector bundle as the twist of a Higgs bundle. Okay, we know that by our local global comparison, such form always exists locally, right? Such thing always exists.
Sorry, is
Is there like a sentence maybe? Sorry, you say such that blah blah blah. What is there?
Yeah, I haven't stated the whole theorem. I just first state the condition. Okay. So we have, if we have such a condition, then we have. The idea is that we can use the local correspondence because although we didn't have any global correspondence yet, but we have already local correspondence. So we could use the local correspondence, give us the local vector bundles Higgs field. The question is that this might depend on the toric chart you chose. So the claim is that although you could use the local correspondence to define locally Higgs field here, but it does not depend on any toric chart you chose. So the statement is formally like that. So when we restrict this canonical Higgs field to this open, then we use this lambda isomorphism given in the condition. Then this lambda isomorphism will interpret this canonical Higgs field to the local Higgs, to the Higgs field like that. Because E is a Higgs bundle, as I assumed. So we can have so namely, when you twist this canonical Higgs field by lambda, then it will give such an interpretation by just sending the Higgs field on E to that. Okay. Is it clear?
Wait, so can you reverse engineer this to, like, if you just started off with a pro-étale bundle, can you find like a P out of this?
If I start with the pro-étale bundle V, then by the local global comparison, we know that étale locally, it has such a form. Then étale locally, I define this theta V like this, like the Higgs field acts on the corresponding local Higgs bundle, then it will give you geometric Sem operators. And locally, it defines like that. And the claim is that this does not depend on the choice of your local charts.
Sorry, I'm asking, like, let's say someone came and told you without knowing any of the theory, that there was this theta V acting on every pro-étale bundle. Would you be able to reconstruct the V out of it? And the LB, so on?
But you have to put some conditions on your canonical Higgs field, right? I mean, if you just came up with the canonical Higgs field on any pro-étale vector bundle, but you do not give me the compatibility with local correspondence, I don't know what to say about it.
Sorry, I'm just asking a dumb question. Let's say the canonical Higgs field is the same one that you're constructing. I just don't construct it through the local correspondence. Do I then get to reproduce some aspects of the local correspondence? Like, do I get to build my spectral cover B and maybe this is too big. I can ask after.
Yeah, maybe in the last corollary you will see something similar. I don't know if that will answer your question. Okay, so let's see later. So any other question about this statement?
Yeah, so do you mean if you have a canonical Higgs field, then how one construct a correspondence?
Right.
Yeah. Then that we will see in the last corollary.
Okay.
Yeah. Okay. So proof. So we only need to prove that if I have two isomorphism like that, I would like to compare the Higgs, the geometric semi-operators they defined. If I have two things, and we need to prove they define the same Higgs fields on the restriction of their intersection. Okay, so in fact, recently similar things proved in Camargo and my work by explicit computation using Farting's extension. So here we present a new proof by Heuer, where he encodes the explicit computation into the local global comparison, because here Farting's extension appeared. So then it will make the new proof very conceptual, very nice. So we will see it. So we need to compare the Higgs field they define. So first we make some simplifications after replacing U1, U2 by an p-adic cover of this thing. We may assume that U1 is equal to U2 equal to U, and they are affinoid with a toric chart. And we can moreover assume that E1, E2 are CF plus small. And the second simplification we would like to make is that we may assume that we may assume that those pi are equal to each other, and also L1 is equal to L2. Why is that? Because here TU, so here by assumption B1, B2 . modules over curly B1 and B2, and it factors through the endomorphism of the Higgs modules. So we just consider B to be the product of them, and the L to be the product of them. Then we still have the alternate log image is equal to the theta B1 times theta B2, which is just the theta B lies in the global section. Sorry. Lies in the global section. Okay, so we may do those simplifications. Then the key ingredient will appear. So then we have the following situations. So V as a number one isomorphism to pullback of E1 tensor over B with L, and we have a number two isomorphism of B2 times B over L. Okay, by local global comparison, we know that there exists U prime to U étale cover. Such that if I restrict to U prime, then we have natural isomorphisms of them with our E1 theta 1, E2 theta 2, right? So after making these simplifications, we may assume B1 is equal to B2 and L1 is equal to L2. And by restricting our U to a further étale cover, then by local global comparison there, we know that this is isomorphic to local correspondence, and this is also isomorphic to local correspondence. And this is a natural isomorphism because we only vary E1 and E2. Okay? Okay, so here comes the key ingredient of the proof, is that we consider the composition of these two isomorphisms. Number two composed with number one inverse. Notice that as this local Simpson correspondence is an equivalence. So there exists a unique isomorphism of Higgs bundles. Phi from E1 E theta 1 to E2 theta 2, making this diagram commutative. Namely, such that this is equal to lambda inverse composed with lambda 2 composed with lambda 1 inverse composed with lambda. Okay, this diagram is commutative. Here we use the local correspondence as an equivalence. Okay, so now we just make some transformation of this equality. Then we know that lambda composed with this one, composed with this one is equal to 2. Okay. Since this lambda is natural in E theta, so by definition, this will be just you pullback of this phi tensor. Okay, so namely, this is equal to mu pullback of phi. Phi is an isomorphism of Higgs bundles in the tensor with the identity map. Okay. So now we can conclude. Finally, we have B lambda 1 isomorphic to this thing. And locally, it defines the definition using their theta 1 to give the Higgs field is like that. And it gives back to C prime of B. Okay, similarly, we have the following one. Number 2, I'm splitting it L to this one. So here I present two definitions using two different local isomorphisms. And I would like to see this diagram is commutative. So in fact, because we have using the local correspondence to produce an isomorphism of Higgs bundle. So phi is the isomorphism of Higgs bundle. So this map, this diagram is commutative. And also this diagram is commutative. I'm sorry, because phi is an isomorphism of Higgs bundle. So phi commutes with θ1 and θ2 like this. So this is a commutative. And they commutative by the definition of phi because this is chosen to be lambda 2 composed with lambda 1 inverse. So they commute. So we see that the two definitions of geometric Sen operators coincide with each other. Okay. Any question?
Sorry, could I ask you probably about the statement? I probably misunderstood something, but in your local setting, you seem to have equipped any small pro-étale bundle with a Higgs field.
No, I didn't assume they are small.
No, but in your local setting, right? For small ones, you did construct the Higgs field. Sorry, something which you already erased, which you explained before. With the choice of term.
Yeah. In the further simplification, I can assume you1 and u2 are small.
I'm just asking about the statement.
Mm-hmm.
Could we rephrase the statement as saying, without ever mentioning V, but just saying that this theta V coincides with that local construction on U primes where the bundle becomes small?
Yeah, I think so. Yeah, but this is more general, I think. This is slightly general because then you just restrict to small vector bundles. Yeah, anyway, yeah.
Okay.
Because local correspondence will give you that's a comparison isomorphism, right? So this is slightly general, right? Yeah. Any other question?
So you define a Higgs field by gluing local correspondence?
It's not like a gluing. It's just like they coincide with each. Yeah, it's a glue. Yeah.
I just understand. If I coincide with Camargo's Sen operator. Higgs field.
Yeah, I mean, this is obvious from the construction. As I said in the beginning, the geometric Sen operator is just in any context of p-adic Simpson correspondence, it should correspond to the Higgs field. So if Camargo follows that philosophy, then it coincides with his construction, right? So at least I can ensure you that it coincides with my construction. Okay, so we move to our last calorie.
So you have already defined this theta v?
Yeah, because locally everything is small, so I can use this local comparison isomorphism to give a non-canonical definition of geometric Sen operators. And I claim that this definition does not depend on any choice of charts and the isomorphism you chose. So it's a canonical definition.
I'm just confused because your this Higgs field is defined over the theta v is defined on the pro-étale side.
Yeah.
But you were just talking about étale.
I mean, if locally we have such an isomorphism, so the Higgs field over E can be pulled back to the pro-étale side. So it's
But am I right? Maybe not. That even in the local case, you need to use this L and B.
I'm sorry?
I was just trying to understand what Sasha said. Is it true that like in the local case, you still need to talk about this P and L to define?
Otherwise, we couldn't make sense of this part, right? Anyway, I'm sorry. In the local case, you can omit this part and only use these two to define non-canonical Sen operators. As I said in the beginning, as long as you have a suitable context of p-adic Simpson correspondence, then the Higgs field action here will give you a Higgs field action on the corresponding vector bundle. Right?
Okay, sorry. Okay.
Yeah.
Thank you.
To formulate even the theorem, just use the local correspondence.
Yeah, yes, but as I said, this is slightly this formulation is slightly general than using local correspondence because every local correspondence have such a form. So yeah, and I prefer this. This is more conceptual. I think. Using twisting, the idea of twisting.
It's more general in the sense that you get this compatibility for a larger class of U primes. Than those where they
yes.
Small.
Yeah, and I think the proof essentially only used this, right? Yeah. Okay, so we move to our last corollary, which will implies the essential subjectivity of the global Simpson functor. Namely, we would like to use this geometric Sen operator to recover the Higgs bundle from a vector bundle. So, corollary, let U be a smooth rigid space over K, and V a vector bundle on U pro-étale. And we take B to be the image of theta V. So theta V is the geometric Sen operators associated to this pro-étale vector bundle, or the generalized representation. So L is an invertible B module on U pro-étale with state law image is equal to the canonical element.
Sorry, where does B live?
B is an OU algebra. I'm sorry. OU algebra.
On the pro-étale side.
No, étale side. OU algebra on U étale.
So you restrict B to the étale side first and then do this.
Yeah, maybe it's better to mention first that how to say? How to say? Because as we see, I claim that this is a étale coherent OU module, OU algebra. So first, I claim that this is Adala OU coherent algebra. Why is that? This is a statement Adala locally. So locally, I can use the local Simpson correspondence to see that this is isomorphic locally with the endomorphism of corresponding Higgs bundles. So Adala locally, it is an OU coherent algebra. So globally it is also. Okay. Sorry about that.
Wait, so you're not claiming that it's in the morphisms on the pro-étale side is the pullback of some étale bundle?
Yeah,
Rather,
and also it is the push forward, right?
you are claiming that.
I think he is claiming that, because like locally, it has this form nu upper star V tensor L, so it takes kind of more.
Yeah, or I could say this. So I prove that this. Sorry, maybe the arrow is. So this, I claim that this is an isomorphism, and you can check Adala locally, okay? You can check Adala locally, and the Adala locally, we can use the local Simpson correspondence to see that locally it is equal to the endomorphism of a Higgs bundle, and the endomorphism of Higgs bundle is a coherent OU algebra, okay?
So it means that like push forward to pull back and there.
I mean, push forward and pull back is, I mean, isn't it a very, so this map should be fully faithful, right? Fully faithful, right?
Wait, end OV, like you. Sorry, I mean, if that's nu upper star of something, doesn't that mean it's like a previous?
It's like what?
Sorry, end OV of V.
OU, I'm sorry. And OU of V?
Is that V tensor V dual?
Yeah.
Then I'm confused. Isn't that like saying that it's nu upper star of something?
Yeah, that's what he's saying, right?
Yeah, but I'm confused about.
I mean, it seems more probable that the right-hand side is the morphisms which commute with theta.
Yeah. But when you write like saying that's the same as end E theta, right? Like, aren't the ranks different? Like if V is a rank D vector bundle, rank V is a rank T squared thing, and the morphisms of something that commute with the Higgs operator is probably much
So this is an endomorphism of pro-étale vector bundle.
Then what kind of object is that?
What kind of object is that? Is the endomorphism of?
Is that a rank D squared vector bundle on the pro-étale site?
I mean, this is just the sheaf of.
Should be this really defined as just the sheaf on étale side?
Okay, so maybe I should. I don't know. Yeah, maybe it's better to write it like this.
You just define sheaf on each U prime to U, you restrict to your V to U, like U pro-étale U prime takes the global endomorphism.
Okay, maybe I should write this OU like V upper star OU or. No.
The statement that some isomorphism is false, but the thing on the right is the thing that you want.
Yeah. Yeah, that's
Yeah, I think in Heuer's paper, he usually mix Adala and the pro-Adala. As long as things lives in Adala, he used the fully faithful to regard it as an Adala sheaf. So yeah, so the canonical element is here. Recall that as long as U is proper, then Heuer's rigidification give you a compatible system of choice of such invertible modules, so satisfying these properties. But this theorem is still true for non-probo case as long as we assume there exists such an invertible bundle. Then we define E to be the V twisting by this L inverse. And this is this more precisely comes from a vector bundle over U et endowed with canonical Higgs field. Theta V, the geometric Selm operator. Okay. So namely, we are constructing this S V is just we call that S inverse. Previously, we only consider S inverse is this one. So it's better to So this corollary allows you to construct the inverse of S.
I feel this canonical Higgs field might be zero.
No. It can be endowed with such a Higgs field. Right? I know what your concern, but I'm defining a Higgs bundle from a vector bundle V.
You mean this E can be equipped with a Higgs field?
Yes.
I'm asking whether the canonical Higgs field of E itself is zero.
Canonical Higgs field of E. It's an adaptive vector bundle,
okay, if it comes from adaptive vector bundle, it means equivalent to say it has zero canonical Higgs field, right?
Yeah.
Okay.
So in fact, this theorem tells you that how to read from a vector bundle to how to produce from a vector bundle over pro-étale site a Higgs bundle, like that. So in fact, we are defining the p-adic Simpson functor. So proof. So the problem is data local. So hence we may assume that there is a toric chart. And the V can be write as a local correspondence of some Higgs bundle, A prime, theta prime. And we put E prime, the image of theta prime T U to in the morphism of E prime. So after replacing U by its toric tower, we may assume that there exists a invertible module L prime with agitate log image, which is theta B prime. And the theta B prime is just the theta prime lies in the B prime. B prime is something of tensor with endomorphism of E prime. Okay. So after replacing this, we can find this. This is just the remark of this local global correspondence, local global comparison. Okay, so by local global comparison, there exists an isomorphism lambda from V to the pullback of E prime and twisting by L prime, okay? So, I will finish in 2 minutes. Okay, notice that if I push forward endomorphism of V, so it's isomorphic via lambda with endomorphism of E prime, E prime. And we have TU action through theta E prime and theta V. By the definition of theta V, we know that this diagram commutative, right? Because every theta V, how to define theta V is that you pick such a isomorphism, and the Higgs action for that will induce the geometric sum operator. So by definition, by construction of theta V, this diagram is commutative. Okay, hence lambda induces an isomorphism of the image of these two maps, isomorphism from B to B prime. So we have E is the pullback of push forward of V and twisted by L inverse, which is just the pullback of L prime hence over B, L prime hence over B, this one, okay? Notice that as the log, HT log image of this twisting is equal to theta B prime minus theta B, but B is equal to B prime, so this is equal to 0. And then finally, by our multiplicative Hot-Taylor sequence, if you have a bundle here, whose image is 0, then it comes from an Adala bundle. So is Adala bundle, and so is E. Because E is just that. If they are coming from Adala thing, then this is also an Adala vector bundle. So this proves the theorem. By twisting, you can recover a Higgs bundle. So I will stop here. Thank you very much.
Thank you so much. Are there questions or remarks?
I have a probably stupid question. Sorry, the name B suggests that it should be some kind of period ring. Does it make any sense? Or not?
No. B is not a period ring.
Okay.
I would like to regard B as a closed subscheme of a possible period ring.
Sorry, say it again.
I would like to regard B as a closed subscheme of spectrum of a period ring, but it's very vague. So
Do you know why the name B is chosen?
he's in base, base, I think.
Because A was already taken. Okay. More questions?
So in this correspondence, on the right-hand side, you can multiply Higgs field by, say, p to the n.
Yeah, that's a very brilliant observation. There is a autofunctor sending that. Yeah, previously I would like to use this property to establish the p-adic Simpson correspondence, but I failed.
But is it clear what I'm supposed to do on the left-hand side?
The left-hand side, yeah, it's very complicated. I don't know what to do with it. Yeah.
It's going to depend on all these choices, right?
Yeah,
But at least in the current case, one can canonically define this action.
Yeah, in the case of curve with genus bigger than 2, I think that thing has a canonical rigidification rather than Heuer's rigidification, so that the compatible system of LB is canonically chosen, right?
Maybe I should withdraw what I said.
Think about that later. More questions for now? Okay, if not, then let's thank Tongmu again.